Bonjour, merci d'être venu. Thank you for coming. So last time we discussed the Lindard function, which is this bubble, or if you want, it comes from this. And you will see that it plays a very important role in the electron gas. So even if it's for the non-interacting, it turns out that it's rather, it determines a lot of the properties of the electron gas, even in presence of interaction. So today well, the program is very big. I don't think I will do all this. But I will start with some simple discussion on what we expect. What is the expansion parameter when we have Coulomb interactions, and the phenomenon of screening, that's very very important. And I'll discuss something that looks a little bit strange here with reducible and irreducible susceptibilities, but it will become clear again a little bit later. And plasma oscillation is another very important thing. Then we'll basically recover the same thing, but by doing diagrams. So there will be the random phase approximation. And as a consequence of the dielectric constant, I will discuss how the interactions modify the particle-hole continuum, that's this quantity, how you get the screening at omega equals 0 and Q goes to 0. What are Friedel oscillations? This I will not derive in detail, but I'll tell you the result. To derive this, it takes the full Lindard function that I did not compute completely. And then I will show you that there's a plasmon here that's a collective mode. I will show you how it comes about. Actually, already here, you will see it come out. And we will see that the F-sum rule that I've discussed before is at Q equals 0 is satisfied by the plasmon. So plasmon has all the spectral weight at Q equals 0. Okay, so that's the program. Do you have any questions? Okay, so what is the expansion parameter? Well, the expansion parameter will be a potential over kinetic energy, and we want something typical. So potential energy will be E squared over 4 pi epsilon 0, and then some characteristic distance here. The characteristic distance is 1 over the Fermi wave vector, because the Fermi wave vector is related to distance between atoms. And then the kinetic energy is h bar square kf square over 2m. So this, in other words, this basically is 1 over kf times a mess here. Let me drop all the constants. So I have me squared. Well, okay, I can keep 4 pi epsilon 0. Me squared 4 pi epsilon 0, and then there's h bar square. Okay.
There's our time too.
Yeah, I'm dropping all the constants. Well, not I keep this. I'm cheating a little bit. So this has to be dimensionless, right? So it means that this has dimensions of 1 over distance. So this is 1 over kf, some distance a0. So you know what this distance is, a0?
Hydrogen bond length.
It is what?
Is that a parameter 0.53 angstrom?
It contains only fundamental constants, right? So this a0 is the Bohr radius. So it's the typical size. Typical size of atoms, right? So if I write h bar square k square over 2m, and then for k square I take I use Heisenberg and I take a0 square, and so this should scale as E square over 4 pi epsilon 0 times A0, right? So you see that A0, so A0 is H bar square over 2m times 4 pi epsilon 0 and is divided by E squared. So perhaps I missed factors of 2 and so on, but I mean, the idea is that this A0 is half an angstrom. Is this 2 there? Do you know? Look at the note and tell me if this 2 is there. I think it's not there. But anyway, I mean, the important thing is that this is a typical size for an atom. Okay. So now what we want is a dimensionless parameter for the expansion. So this is a dimensionless parameter. But well, it is customary to define the expansion parameter slightly differently. So what we say is that the density n is equal to so one atom divided by 4 pi over 3 times Rs times A0 cube. Okay, so in other words, it is if Rs times A0 is the interatomic distance, right? Then the density is you have one atom per volume of one atom. Okay.
So shouldn't you divide the volume by this?
Well, the density is as units of 1 over volume, right? So this is fine here. I have A0 cube. If you want, you can multiply by n and divide by m, right? So n times this is the volume, and the density is n divided by the volume. So the n drops out.
Yes, okay.
So that's the definition of Rs. That's our expansion parameter. Rs. So if you want, this n is kf cube over 3 pi square in 2 dimensions, right? So that's how I get Rs is 1 over kf A0. Numbers. I mean, I will not carry all these constants in what I do now. They're all in the notes, but the constants are not so important. I just want to know how things scale. Okay, so n is kf cube over 3 pi square, and it's also 1 over the typical size of an atom. So you see that I get Rs scales like 1 over kf A0. Okay. Now, okay, so let's keep this piece and erase this piece. Now, Thomas-Fermi screening. So what is the Thomas-Fermi screening? So the Fourier transform of the Poisson equation, right? Grad square phi minus grad square phi is equal to rho over epsilon 0. So if I take the Fourier transform of this, and I write for rho, I write rho external plus delta rho, the induced rho. Then what I get for the Poisson equation in the Fourier space is that minus q squared. So the potential phi of q and omega is equal to 1 over epsilon 0 times rho external. So I will write this as rho e. Okay, this is a charge I have outside. But what I need to put on the right-hand side is the total charge. Okay. So there's a charge that's induced. So this rho e perturbs the system, and the system responds, and there's some charge as well. So so I will write this as minus chi rho irreducible. We will see why I call it irreducible of q omega times phi of q omega. Okay, so it's I'm using linear response theory to write that this is delta rho. And if you look at what we had for because the coupling between the potential and the charge is phi, so this is linear response theory. And here you see I write the response to the self-consistent field. Okay. So what do I have here? I have that, and this is plus now. When I take the Fourier transform, the plus disappears, the minus disappears. Okay. So what I get is that phi of q and omega is equal to 1 over epsilon 0 times let me do it more slowly. So I have this times q squared plus 1 over epsilon 0 times the square of the charge times the density. Okay, here is the charge, but now I transfer this into density, irreducible of q omega, and that's equal to 1 over epsilon 0 times rho external of q and omega. Okay, so I can write this as phi of q and omega is equal to 1 over epsilon 0 times q squared plus this combination. Okay. So this combination, I will take the omega goes to 0 limit and q goes to 0 limit. And in the sense that the dependence of q here is over the scale of the Fermi wave vector. And I'm looking at long wavelengths. Okay. So if I take this quantity, then you see that's the response to a change in the self-consistent field. So that's like the change in density due to a chemical potential shift, because a scalar potential goes into the chemical potential. So this is E squared, and I will show you this explicitly actually later. So it's E squared over epsilon 0 times dn d mu. And another way to see this is that at omega equals 0 and Q goes to 0, this is like a thermodynamic sum rule that we discussed earlier. And times rho external of Q and omega. So you see that I have Fermi wave vector. So that's called Q square Thomas-Fermi. That's equal to E square over epsilon 0 times the dn dv. So if you take the Fourier transform of this, if you put Q square Thomas-Fermi here, if you take the Fourier transform of this, what you will get is that you get an effective potential V of R that is proportional to 1 over R, like the Coulomb interaction, but times exponential of 1 minus Q Thomas-Fermi times R. Okay, so the Coulomb potential is screened now. It's not 1 over Q square. It's 1 over Q square plus Q Thomas-Fermi square. And if I take the Fourier transform of this to go back to real space, I find that I'm damped this way.
Just a quick question. You're assuming here that dn over d mu is positive. Is it always the case?
If it is not, there's an instability. So dn d mu is positive, is one of the convexity relations of thermodynamics. When dn d mu is negative, there's a phase transition.
All right. Okay.
The system is indeed, you're right, I mean, is indeed unstable. So I'm assuming that I'm in a stable system. Okay? That's a nice question. So since we will use this momentarily, here I erased something I didn't want to erase. So RS scales as 1 over KF A0. And now you see that I can define a dielectric constant. So, or starting from this if you want. So epsilon longitudinal of Q and omega is equal to epsilon 0 times 1. So you see, to define a dielectric constant, what I need to do is to factor Q square here. Q square, or let me do it here. Because that's what I will do. So I factor Q square, and then this becomes 1 plus 1 plus this over Q square. And then you see that epsilon longitudinal of Q and omega. Okay, I get 1 over epsilon 0 Q square times the dielectric constant. That's the definition of the dielectric constant. Okay, that's what multiplies the 1 over Q square. But the dielectric constant depends on Q and omega. So it's epsilon 0 times 1 plus this. And what is this? That's the Fourier transform of the Coulomb interaction. Okay, so I will write this as V of Q times chi irreducible density of Q and omega. So that's one expression for the dielectric constant. And I will show later that this is indeed the NDV. So one last question I want to ask is, what is this distance? You know, how does it scale with RS? So again, I will not put all the constants. I will just do things in a very sloppy way. So the distance lambda is 1 over, well, lambda square is 1 over q Thomas-Fermi square, okay? If you look at this. Now, so if I put this backwards, this is like epsilon 0 over e square. And the n d mu is what? It's backwards now. So it's d mu dk Fermi times the dk Fermi dn. Okay, I just use the chain rule. I express mu in terms of k Fermi of n. Now, mu is like the Fermi energy, so it goes like kf squared. So I have epsilon 0 over e squared, and that goes like kf squared. So I'm left with kf when I differentiate, and this goes like kf cubed. So this goes like 1 over kf squared. So, and here it's kf over m. So this means that this is 1 over kf. And if you remember the definition of A0, this is A0 here. Do I have this right?
Yes, it's the right dimensions.
Okay, that's A0. Okay, so this has the right dimensions, right? A0, kf is 1 over distance, so this has the correct dimension. So now if I so remember, we just want to see how it scales with with A0. So it means that we have that lambda square goes like A0 square times kf A0. In other words, it goes like, I wrote it like this. So it goes like A0 square times Rs. No? And A0 times Rs, we said, is the distance between atoms. So let me write this as lambda, the distance, the screening distance lambda is A0 times Rs over square root of Rs. Okay. So lambda is like the distance between atoms divided by the square root of Rs. So if Rs is less than 1, less than unity, or much smaller than unity, means that the screening distance is large. Remember that Rs was the ratio between potential and kinetic energy. So if Rs is small, means that we have a good, we're expanding in powers of the potential. So so this is fine. Rs is small means that we are doing a right expansion, and the screening length is relatively large. But if Rs is very large, then it means that the potential energy is large. So the expansion is not so well defined, and if Rs is very large, then the screening distance becomes very short.
So the screening distance corresponds to the distance at which electrons do not see each other anymore?
That's right.
So if it is small, then electrons do not see each other.
Yes.
Okay.
Well, or they see each other only at short distance.
So you're saying that if the potential energy is large, then electrons do not see each other if they are
No,
close to
if the
each other?
potential energy is large, what that means is that the kinetic, or the other way to see it is that the kinetic energy is small. Okay, if RS is small, RS is potential over kinetic, right? So if RS is small, there's lots of kinetic energy. Why is that? Because of, if you look in quantum mechanics and you confine things, then because of Heisenberg, the kinetic energy increases. Is that clear? No? If I put electrons in a smaller distance, then the kinetic energy is large. So it's a little bit paradoxical. I mean, it means that if I make the system more compact, potential energy is less important. But it's less important. Why? Because kinetic energy increases. That's the right way to see it. Okay. So if RS is small, then this screening distance is large. Okay, and it's because the electrons have lots of kinetic energy. Okay? Does it make sense? Okay, this is a good question. Okay, reducible versus irreducible. What do I mean? I mean, two different ways of writing the dielectric function. So instead of looking at the, if I go back to Poisson equation, so Q squared, phi of Q and omega is equal to 1 over epsilon 0 times rho external of Q and omega. And now for the induced charge, let me write the charge correlation function, not the irreducible one, as a function of Q and omega times phi external. Okay, so this time, instead of having the self-consistent field phi, here I look at the response to the external potential. In other words, the potential caused by this charge. Is the difference clear? Okay. So if we do that, we know what is the we know what this is, this phi external. Okay, phi external is just equal to 1 over epsilon 0 Q squared times rho external. That's the definition of phi external. That's the potential that's induced by the external charge. So you see I have another expression for the for the dielectric constant. So if I do the same thing as I did earlier, you see that phi of Q and omega here is 1 over epsilon 0 Q squared times 1 minus, and then I will have times times rho external of Q and omega. Not very good. So this is this guy here times this. So again, rho I write as in terms of density fluctuation. So here I have E square over epsilon 0 Q square times chi and n of Q and omega. So I have another expression for the dielectric constant. I have that 1 over epsilon L of Q and omega is equal to 1 over epsilon 0 times 1 minus, again, this is Coulomb potential, minus V of Q times chi and n of Q and omega. And these two quantities need to be equal, okay? So we will see what I mean by chi irreducible just by equating these two things. So if I equate these two things, you see that I have 1 minus VQ of chi and n is equal to 1 over 1 plus VQ times chi irreducible and n. So it's a KQ, Q and omega for sure. So it means that VQ of chi and n is equal to 1 minus 1 over 1 plus VQ chi irreducible and n. So this is equal to VQ times chi irreducible and n over 1 plus VQ chi irreducible and n, which means that I have this formula now, which is that which is just that chi and n of Q and omega is equal to chi irreducible and n of Q and omega divided by 1 plus V of Q times chi irreducible and n of Q and omega. Okay, so what it means, irreducible, is that it means that if I look at the if I just do an expansion in powers of the Coulomb potential, I get that this is chi irreducible times minus chi irreducible V of Q times chi irreducible plus etc., right? So in other words, in terms of diagrams, it's as if I have, and that's why our Lindorf function is important here. Means I have this minus, again, this diagram times the interaction plus plus, etc. Okay, so you see that this susceptibility, this piece here is irreducible in the sense that I cannot divide the diagram in two by cutting a Coulomb interaction. Okay, so it's irreducible with respect to the Coulomb interaction. Okay, that takes the Coulomb interaction, the long-range part of the Coulomb interaction into account this way. Okay, plasma oscillations. Okay, plasma oscillations, it's the same as you saw in classical electrodynamics. I mean, it's just the fact that if you displace, think of capacitor plates and you charge it a bit on one side, then there's a constant electric field that's set up, and you will have oscillations. So, in other words, if I write dj dt is equal to minus ne dv dt, and this is equal to n e square times the electric field divided by the mass. That's just Newton's equation. So now if I take the divergence on both sides, the divergence of the current is minus the derivative of the charge with respect to time. So I get minus d rho squared dt. And here I get n e squared over m. And the divergence of the electric field is what? Is the charge density divided by epsilon 0. Okay, so clearly this is just an oscillating solution. And I get the plasma frequency. That's an important result here. Omega square plasma is equal to n e squared over m epsilon 0. Okay, so that would be this frequency. You know, when we do things in more details with all this formalism here, we'd better find this plasma oscillation here. Okay, so now let's take into account the interaction using diagrams. That would be the random phase approximation. Okay, so we start with this here, and we take as a first approximation of this irreducible in the particle hole channel with respect to cutting two lines like this that go in opposite direction. So we take the functional derivative of this sigma with respect to g, and we saw that it gives simply this line and this line there. So with this, we have that these 2 points are the same. These 2 points are the same. And in the case of this diagram, then it's the other way around. It's these things that are the same and these things that are the same. So it means that we have this, and then if we have some momentum q here, this is k plus q, and this is k, and this is equal, okay, with that's the full thing. is equal to this. Whoops. Equal to K plus Q. And then plus this, so that's plus this times this line here times this guy. So again, we have K plus Q, K, and well, yeah, K prime plus Q, K prime. And then there's this this one here with a minus sign. So there's minus K plus Q, K. And then I have K prime plus Q, K prime. And then I stop here. Okay. So here there's a momentum Q that flows, okay? So here I have V of Q. But here I have what? I have V of K minus K prime. Okay. So if you keep this term, it's called a generalized random phase approximation. But what we will do is the random phase approximation. So in the random phase approximation, we neglect this. Why do we neglect this? We neglect this because here you see that when Q goes to 0, this is divergent. We get 1 over Q squared here. Here we get 1 over K minus K prime. And we're doing three-dimensional integrals over K and K prime. Okay. So phase space, if you think of integral d K minus K prime cube and 1 over K minus K prime square, you see that the phase space is such that there's no problem. It converges. Okay. But here there's a problem. So we keep these terms and we neglect these ones.
So we keep the term with problems and leave the term without problems?
Pardon me?
So we keep only the term that has problems?
And we keep only the term that gives divergent contributions.
Okay, right, yeah.
Okay. That Q goes to 0. Yeah, I should have said it this way. That's the most important part. So if we do that, we neglect this. Then remember that this was minus chi. So minus chi and n of Q and omega is equal to, this is minus chi 0 and n. That's the Lindard function that we computed of Q and omega. And here I have two minus signs, one for this, one for that. So that's plus VQ times the chi 0 and n. I won't write the Q and omega because I'm running out of space, times the chi and n. Okay. So this is plus minus. You see where I'm going now? So I have 1 plus V of Q times the chi 0 and n of Q and omega times the chi and n of Q and omega is equal to chi 0 and n of q and omega. Sounds familiar? Okay. So now you know what I mean by irreducible. I mean, here it's completely general. It could be in high order in perturbation theory. It doesn't matter. This is correct. But so in this random phase approximation, this chi irreducible is just chi 0. That's just the Lindard function. And you see why it will be important then. It's because we can compute the interacting dielectric constant in terms of just the irreducible thing. So we can get screening from this, and we can get the plasma frequency from that, and we can get also the Friedel oscillations, and I will show the F sub rule also. Okay. Do you have any questions there? Okay. Okay, so now let me, before we talk more about the dielectric constant, let's just talk about this this particle hole continuum. So that's the last thing I will have time to do here, and this plasmon pole. So you remember that this was the domain when we had this piece here. This was the domain of where the imaginary part of chi 0, or chi 0 here. This was the place where the imaginary part of chi 0 was different from 0. So what happens in this case? Let's say that I have here I have, let me write this as x plus iy, and this is 1 plus a constant times x plus iy. So I want to take the imaginary part of this to see how it compares with what I had there. So the imaginary part of this is what? Well, it's just equal to y divided by 1 plus ax squared plus y squared. Okay, I multiply by complex conjugate numerator and denominator. And when I take the imaginary part, that's all that's left. The real part is more complicated, but for the imaginary part, that's all there is. Well, I mean, there are some constants, but okay. So if I look at the imaginary part of this, let me write this as chi prime prime just to make this a little bit shorter. Chi prime prime of q and omega is equal to, so I will write chi 0 now. So chi 0 prime prime, and n of q and omega divided by 1 plus VQ times chi 0 and n prime. Okay, so the real part of Q and omega square plus chi 0 prime prime and n of Q and omega times V of Q square. Okay, so suppose that there's a pole here of this. Suppose that I have a contribution to a chi double prime. Yeah? So this is, suppose I have a pole here. then the pole here will be canceled by this one because it's square. Okay? So the poles are shifted now. The poles are where this is equal to 0 and this is very small. Okay. So let me take just a simple case with three poles. There's positive and negative, so I have 6 poles. So there's omega here, and I have poles, let's say here, here, and here, and the function is odd. So there are poles also in this section. So in other words, I have assumed that chi double prime is has just there's just 3 modes in the system, and or yeah, I mean 6 because it's on the both sides. So that there are 6 poles. Okay, so now if instead I want to know what are the places where this is 0? Okay, to find where this is 0, oh my God, no more space. So to find where this is equal to 0, so you have to remember I have 1 plus V of Q times the real part of chi prime. So chi prime, the real part of Nn is equal to, let me put omega. Let's forget about Q for now. So that's the integral d omega prime over pi of chi double prime of omega prime divided by omega prime minus omega, principal part, right? So now this is an odd function, which means that I can write this as I can multiply by omega prime plus omega, numerator and denominator, and I will get this, and that's it now. Now suppose that omega prime chi double prime is these has these 6 delta functions. I mean, yeah, you need the 3, and then it will reflect on the other side. then I can easily write what this object is, and it is very late, so I'm not sure I can do this properly. But you know, if this can be written as sum I equals 1 to 3. In fact, I can put everything together of some number AI times divided by UI. So that's the position of the delta function here of the folds. So UI squared minus omega squared. Okay, and then what happens is this. So I will not have, I mean, I will come back next class because this is, this will be botched. I mean, I cannot do this properly, but if you just use this form, you will see that with this guy, it looks like this. And then I have to put this equal to minus 1 over V of Q to find the places where 1 plus the real part is equal to 0. So that means that I have to look at the intersection with this line here. So the point is that this was the particle hole continuum. And there has been some shift, but basically the function is non-zero again in this same particle hole continuum. But now there's an extra, there's one solution that is now at higher frequency. I know they have plus and minus omega, so and that's this solution. So I will do that properly on Friday. But yeah, that's you see there are still 6 solutions. 1, 2, 3, 4, 5, 6. So we have not lost the solution. But there's one solution that is now at a high frequency. So this as poles, or this is non-zero at the same place, basically as the non-interacting case, except for one mode that is a collective mode here that is put outside. So I will redo this next time properly. Okay, so any questions? Okay, so I will stay, so I stop recording, and if you have questions, I will be around.